Hey, everybody. Okay, hey, I'm Mike. I'm one of the founders. I'm the CEO of Tecton. Morgan?
And Morgan Su, Director, Data and ML Engineering at FanDuel.
Cool, and thank you for coming. I know this is the, the best time slot of the whole, so it means a lot that you're here. We hope that this is interesting, educational. If you have, very informal, so if you have questions, we'd love to get, chat with you afterwards here or outside, because I'm sure there's another talk. What we're gonna go through today is we're just gonna talk about what we see as a trend of a lot of companies. A lot of companies are going through this journey of figuring out how do they use data in their companies. And okay, so that's us. And so they're trying to build these more magical experiences. So let's take time machine, go back a little bit. In the 90s, we had a lot of manual-based segmentation. So you're gonna want to have a personalized experience for somebody. You're literally writing this person should get this experience, this person should get this experience. Many years later, there was we started having personalization built into our products, right? This is when ML started actually getting into production a little bit. And so a lot of products that we all run here today are have this proto-personalization kind of stuff. And then we started seeing, more recently, these real-time predictive products. These are things that respond interactively. So they will respond, there will be a recommendation that responds to what you just did in this session. Or even like a machine learning that happens in a gaming experience where it'll match you to somebody in real time of a exact similar skill set. Or even there are certain products that are only possible if they're powered by machine learning. That happens in real time. For example, in Uber, they have to estimate how long is it going to take a car to get to you, and then based on the estimate of that, then they have to estimate come up with a price, and that is a key thing for the capability of the whole product experience, and none of that's possible without real-time machine learning. So we see companies going on this kind of journey where they start with their data in all kinds of different places, and then they centralize in a cloud data platform. We're at the Databricks conference, so it's a lake house that you're centralizing in. And doing some basic analytics. Got my BI platform in place. I'm doing some dashboarding, various trends. I'm estimating the future. And then I'm starting to do some proto-machine learning. This is some of the stuff that we looked at in the stage 2 before. And this is a lot of the basic offline models that we might use to predict customer value, churn, basic initial productionization of machine learning. And most companies, even the advanced companies that, if we were to say, hey, what are the best companies at machine learning? Honestly, a lot of companies are in this stage. But many of them are starting to break through, right? And they're starting to launch products that really have, that where their customer experiences are infused with machine learning in real time. And it allows them to build qualitatively better, different experiences, customer experiences. So we're going to talk about what those are today. So as an example, and I'm over-indexing on Uber as an example. I used to work at Uber and help build the ML infrastructure at Uber, built a platform called Michelangelo there. Uber, this is a great example. Pioneer in real-time ML. This is a recommendation in Uber Eats where they say, hey, your food's going to be ready for you in this much time. Here's, we're recommending this dish for you, and we can predict how long it's going to take the dish to be prepared and delivered to you. And that's how they have high-quality recommendations, and then they can optimize their revenue based on recommendations that use all these different signals. Lots of machine learning just in this one page. Now we're starting to see real-time ML everywhere. You go to the doctor, they're helping you with, behind the scenes, they're interacting with software to help them figure out a diagnosis. You go shopping, there's recommendations. You're logging into an app, personalization. Swiping, you're making a purchase, they're detecting fraud behind the scenes. Going on Uber, they're detecting and predicting the ETAs, and a lot of use cases in gaming. So what do all these things have in common? They tend to be pretty high value. You wouldn't really be building this stuff if it's not actually adding a lot of value to your business. So, presumably you came to this talk because you have some interest in like putting ML into production and probably some reason to do it faster. And that's probably a thing that drives real outcomes for your business. But there's some other things that are related that are in common across all of this. They tend to just be like literally hard to do. They have the harder engineering requirements. They're more real time, they're larger scale, they're more in production, different availability requirements, SLAs, et cetera. So like, it's hard to do, but it's a higher payoff. And so some common use cases that happen in real time, dynamic pricing, recommendations, fraud detection, a lot of the stuff we just talked about. So, one realization is that when you build these systems, you build an ML application, it's largely not just about the machine learning model. In fact, the machine learning model tends to be, now is kind of the easy part, to train a model and to serve a model pretty quickly. But to get these real-time applications right, you have, they depend on data that is fresh. And it's a requirement that didn't really exist in the previous type of machine learning we were doing. And so the data part of it and the uniqueness of the data requirements for these real-time ML is something that's often overlooked. And we're just going to talk about that a little bit today because it's a key to unlocking these kinds of experiences, these real-time ML experiences. So what does it take to actually build this stuff? So there's a couple things. You're on the ML team at your company. Like, what do we got to do to get some real-time ML, to build a real-time fraud detection, a real-time recommendation system? So there's a functional level. It's like, can we actually literally build this thing? Like, can we build software that works in real time at this and makes these predictions? Secondly, does my team even know how to work together to practically get this stuff done? Like, whose responsibility is what? And then third, organizationally, okay, so my team can figure it out. I know how to work with my engineer or my eng team, but I'm in a bank and we have security requirements and a whole bunch of enterprise compliance requirements, stuff like that. It's really slow in our organization. There's all these extra requirements. Can we do it within that environment? So we'll step through those really briefly, and we'll talk about some of the challenges there. So the first is just literally the functional stuff, the data requirements. What does it take to actually build this stuff? What are the problems we need to solve? So there's a couple things. I'm going to call it 3 things here. One is just these real-time use cases. They have a broader variety of data sources. So now instead of just reading from my warehouse or lakehouse, I'm reading from real-time data. That's the application. I'm reading from a data stream. I'm reading from and my lakehouse. All of those things need to be part of the inputs that go into my ML model in a fresh and up-to-date way. Also, all of this data needs to be managed in a point-in-time historical way where I can go back in time and know what was the value of this data or these features at a specific point in time when the user was logging in, because I need point-in-time accurate historical data to train my model. And so the time management thing is as a whole thing. And then another thing which is a new dimension to this problem is real-time serving. This has to run at scale. This has to run super fast. And everything has to be up to date, right? So I need all of this stuff to run fast enough that when I'm making a prediction, it's using up-to-date data, not data that was processed a day ago, because that could be way too late and compromise the whole value of the whole application. So how do people do this? They bring together a bunch of different pieces of infrastructure. So they build some pipelines on Databricks. I have an Airflow orchestrating something. I have a serving layer. I'm using Redis for something. And you have an eng team. A lot of companies have an ML platform team that are kind of responsible for duct taping this stuff together. And I'm saying duct taping it together to kind of say it in a negative way. Like every ML platform team, they build this stuff in a very kind of bespoke way, and it becomes difficult to scale. And then a year, 2, 3 years later, they're like, wow, this was just we had to grow way bigger than we wanted to because it was too difficult to manage and it's very costly to maintain, and this thing breaks way more than we want it to. And so the standard kind of like, hey, let me solve this problem as it goes along, solve this problem iteratively, incrementally, and intuitively for an edge team, an ML platform team, just tends to kind of lead you down the wrong path. So let's also talk about like at a team level, there's the whole ML problem workflow, right? All the way from coming up with an idea to operating this thing in production. And the core collaboration that you really want to get right is between the data scientists and the engineers. We want the data scientists to be able to iterate quickly without being slowed down by engineering teams, and you want the engineers to be able to support the platform and scale across multiple data science efforts. And what happens today is there's frankly limited collaboration. There's they have to deal with like siloed data. There's lack of standards, centralization. There's no sharing or governance. So it's really hard for people to figure out like how they work together. That makes things really slow. It's hard for me to tell what's my responsibility as a data scientist, what's the engineer's responsibility, and having these systems not be architected in the right way leads to these are high-cost systems, so it can lead to unnecessarily high costs. We build this thing in the wrong way and I got duplicate pipelines running, or because the project goes too slow, I have a really big opportunity cost for some value, some fraud I'm not detecting because I'm taking 9 months to put this thing into production rather than 9 days. And then at the organizational level, not all of these boxes apply to everybody. So you can look at this slide, and there's been a million talks on every single one of these things, but like some number of these boxes apply to your organization, and your ML team has to deal with, okay, how do I build this application in a way that works with the specific requirements from our team? How do we get monitoring on all of this stuff? How do we share and deduplicate these things? How do we control what can go into production? What data is used for which models in production? Do it with the right level of security. So I won't read through all of this. The one thing that I will call out, though, is the very last box, which is the SDLC integration. It's interesting to note that these real-time ML applications, they are part of the production product. They're part of, that lives in the edge world. That is serving, it's part of your application. And so there has to be some fundamental jump from data science prototyping land to production where it's owned by engineers. And whatever collaboration model we choose has to be able to facilitate that. So it's a tough problem. There's new architectures that are needed, new collaboration workflows. There's all these different security compliance requirements because we're now enabling new people to push to production. And then everything is high cost. It can be, if you're working with streaming, real-time data, heavy infrastructure in production, getting this wrong, it can cost you literally a lot of infrastructure dollars. So how do people solve this? So what top ML companies do is they build infrastructure for the data layer of their ML applications. Feature infrastructure, we call it a feature platform. So if you go to any of these companies, but also choose your favorite brands, they have an ML platform team that's building their feature platform. And we built the ones at Uber. I previously worked on the ones at Google. And at our team at Tecton, we have folks from all of these companies who've participated in building all of this stuff. And there's a lot of common patterns and capabilities that these systems have that really speed up people's ability to create real-time ML and enable them to build things that they wouldn't otherwise be able to build. And at these companies, there's literally, if you go to Google, there's literally hundreds of engineers building this infrastructure. You go to Meta, there's hundreds of engineers building this infrastructure. So while it may seem like, hey, I'm going to have my ML platform, my 5-person ML platform team, wire up a couple of things to make this possible, the reality is it's just super hard. This is a problem, we talk about it as it's a problem that you learn that it's harder the deeper you dig into it. And so it kind of just gets worse and worse the more you try to solve it. At Uber, we built this platform called Michelangelo. And so that was basically a model platform and a feature platform and supported a ton of the ML use cases at Uber that I already talked about, so won't spend a ton of time on that. But this is like a multi-year, at Uber we started it in 2015. So we're 8 years in, there's 50 engineers on that team, and you go to that group and they'll say, yeah, we're still working on it. It's still not perfect. We have a lot of things to do. So we built Tecton. Tecton is a company that is effectively that feature infrastructure team made available for everybody else in the industry because it's hard for everybody else to build this stuff. And we want everybody to be able to build these real-time or batch ML applications at a production quality. And so the feature platform allows you to design, build, centralize, serve, manage the ML, the feature lifecycle across an ML project end to end. And so, on our platform, we support all of the use cases we just talked about. There's a bunch of teams that use software that is like feature infrastructure that we maintain or we build as part of Tecton. And these are some of the really top names in the industry, but also a lot of names that are just trying to figure it out. And most of these folks have tried it, and then they're like, hey, we actually don't want to build this stuff on our own. But we have a lot of people who are kind of in this greenfield situation where they're a small team and they say, hey, you know what, let's just choose the right platform from the beginning without going down this expensive path. So I'm going to tell you a little bit about just a brief walkthrough of what does a feature platform do, and then I'm going to hand it off to Morgan, who went through a similar, this journey that we just talked about in the first 2 slides, where they were able to get to that final column by using a feature platform and a variety of other ML infrastructure to really be able to build a lot of different real-time ML applications. So what does a feature platform do? At the very, 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 very reduction version of it, you put in a snippet of Python code that is a feature definition. It's literally a small snippet of transformation code. And what the feature platform does is it turns it into a production feature pipeline. And so the magic is in what is a production feature pipeline. And so what Tecton does is it compiles that feature transformation code into what we call a feature, and then we provision the right infrastructure, orchestrate the right infrastructure, and run that transformation pipeline regularly to continuously compute and generate the feature values, fresh feature values, and then make the feature values available through the common retrieval interfaces that you would need for an ML feature. So what are those? That's reading it in real time. Hey, I got to make a prediction. I need to know what the latest version of the feature is. And then the second consumption pattern for ML features are training data. I got to train my model. I need the feature data to be the exact same at training time. And so, so this is an example. I put in a simple feature definition in Python code, and Tecton has created using your infrastructure. It could be your Databricks, whatever your data infrastructure is, has created and orchestrates the right feature pipelines and corresponding production infrastructure. So what are the parts of this, right? Powerful feature pipelines. This is the obvious part. Turning raw data into feature data. There's kind of 3 types of pipelines to talk about. One is just like a batch feature. This is super easy. This is running a SQL query. This is running a Spark job on your platform. Second is streaming feature. So a lot of people, especially when you come to real-time ML, you have like a Kafka stream of user events or session events or something like that. And so you want to have a feature that represents, hey, how many times has this user made a prediction in the past, has made a transaction in the past 10 minutes, past 10 seconds. If this person's tried to make 100 payments in the past 10 seconds, that's kind of fishy, maybe it's fraud. And then the third is a real-time transformation. And so real-time features are ones that are computed at prediction time. So they can't be pre-computed because the information doesn't exist before prediction time happens. But think of okay, this person's swiping their credit card. Well, we have a feature that is based on where in the world are they? Well, we wouldn't have known that before they swiped the credit card because the transaction didn't exist. So a lot of compute has to happen in real time. So these are 3 pretty different paradigms of compute. And the feature platform makes the kind of the compute and the operationalization and the orchestration of all of these kind of like hidden away from the data scientist. So the data scientist just has to be responsible for writing that Python code. And so what it does, you write the Python code, it handles kind of like the managed feature lifecycle. So what are the things that you need to do for a feature, for a real-time ML application? You want to have it versioned. You want to backfill that feature. You want to continuously compute that feature. And you also want to generate training data for it. You have to serve it in real time, log its values so you can use it for debugging and auditing and potentially training later if you're training on features that you've served. Monitoring it there's two kinds of monitoring too. There's operational monitoring, like, hey, what's the latency for me serving this thing and how often, what is the uptime and any errors? And then there's like data quality monitoring. And all of the sharing and reuse side of it as well. Very common to have multiple, keeping on the fraud theme, multiple fraud models. And you don't want to rebuild all 200 features for every single model. You want a kind of centralized platform to be able to allow you to define that feature once and reuse it across use cases. And so the third part is the feature store. So the feature store represents the storage and the serving of features. So taking in computed features at scale and making those feature values available consistently online and offline, and handling all of the production serving in real time at scale, the kind of like at scale information retrieval for different use cases, and it can be pretty straightforward for some use cases, but also it can be pretty complex for like a large scale recommender system use case. And ideally the feature platform, at least at Tecton, we are on call for this for our customers. So this is hard stuff to do, and it's kind of annoying to maintain and manage all this stuff. So like we don't want our customers to have to be on call and managing all of their real-time infrastructure. We get pinged if something goes down. So what does this unlock for having these capabilities, having these components available to your data science team? It makes it easier for the data scientists to build better features, because they're just going faster, they're making more features and more accurate, and that leads to more accurate models. And then with the managed feature lifecycle, there's less reinventing the wheel, right? You're not wasting time doing the same thing someone else has already done, and that actually matters at like a kind of team level, a team efficiency level. And then even at an organizational level, how do we bring reliability, governance, and reduce engineering overhead to a data science function? Well, we've given them a very, very fast path to get to production, and we've removed the engineer from the kind of the core data science flow from prototype to production. The engineer has become almost like a supporting function for data science workflows. So I'm going to hand it over to Morgan, who just went through a lot of this journey at FanDuel, and he can talk through how it's gone for them, and then I'll be back.
Cool. All right. Thanks, Mike.
Yep.
So first off, just want to I appreciate everyone kind of coming out, listening to our journey here at FanDuel. So now we know what a feature store could be used for. I'm going to walk through a little bit about how FanDuel leverages some of our modern data stacks, and then go through a little bit about how we kind of ventured through applied machine learning. And I want to be specific about applied machine learning, because it does have different challenges there. So, you might be wondering, what is FanDuel, right? So our mission is to make sports more exciting by changing the way our customers engage with their favorite sports teams. We're America's #1 sports book, and we have over 12 million registered users, and we're growing. It's a very big feat. We have a lot of data, and it's going to be quite a long journey in this journey, and we're kind of continuing to see how we can innovate. So I oversee the insights function in our data organization, with teams focusing both on operational aspects on our analytic platform. So when you think Databricks, Redshift, things like that, that's one side of the team. And the other side of the team, some of the core ML engineering, in which we kind of build production-grade internal and external products. Well, the scope of machine learning really comes down to the first data and feature operations. And in here, we're making sure that we're feeding the right data features to our model. The second piece is model operations. We're making sure we're versioning our models and remembering which ones are actually optimal for our business problem. And lastly, essentially what MLOps answers is providing the experimentation process and a path to production. So applied production ML is a very cross-collaborative process. It's something that really requires a lot of different teams to have a successful outcome. So the first thing, data engineering, acquiring the data is the first step, right? And moving that into an analytical data store and something like Lakehouse, having Unity to govern that. The second piece is working with data science, where they'll use those data, find features that are really relevant for the business problem, and essentially leverage some of the data that is acquired by the data engineers. The ML engineering side of things is one where we actually bridge the gap between what's experimentation and what is actually into production. And lastly, product engineering to enhance products by integrating our ML models. You'll see in this cycle, there's a constant loop that requires great cross-collaboration to drive successful releases. So outside of that, there is a process for production CI for ML, right? Usually in a traditional code deployment, you'll see code to release in something like a repo, you'll have commits, and it'll get deployed. But when we look at additional complexities in ML deployment, there's actually feature data versions, there's the code that orchestrate the ML processes, and there's also model assets. So you can see that all of these have to align to really release and deploy into production. So you might be asking, okay, so what are the key challenges that we faced? Well, I think it starts with organizational challenges, right? So ML engineering is still a very new field, and defining an ML practice was one of the things that we had to face. Because FanDuel is a rapidly growing company, it's in a hyper-growth stage, we needed to scale a team in a short amount of time. Given that ML engineering requires different, diverse skill sets, even sourcing engineers that had software, data, infrastructure experience was a challenge. But I think part of that is actually a really great key success factor, right? Having different perspectives on different technologies to really provide that impactful success measure for some of the things that we've released. On the process challenges side of things, we wanted to answer some of these items here. So there was, we wanted to make sure that we provided standards for some of the things that were going on between the teams because we were growing so rapidly. We wanted to make sure that we had lineage and traceability to be able to debug some of the issues that did come up, and how did we find the root causes. And lastly, finding a solution to essentially answer inefficient and manual workflows and backfilling of them, of the data to provide point-in-time correction. So this is kind of where the team at FanDuel has created our ML platform, the OMNI framework. And I'll talk a little bit about essentially what we were thinking about in the last year and the types of things that we built here. So when we're choosing a toolkit at FanDuel, we knew that every tool needed to be a force multiplier and needed to be managed. So with a very small team, very lean, we had to be very selective about the tools that we picked. We needed the tool to change the way that we organizationally approached a problem. It had to be impactful, and it had to make a big differentiator to avoid any duplication. And we also had to make sure that it integrated with our culture and a broader suite of tooling. So at FanDuel, there's many different products, many different engineering teams, and we had to make sure that whatever tool we chose integrated well with others and was able to provide something that worked with the systems that we worked with. So we had a mature data stack tool set. We used Jupyter notebooks, Databricks notebooks for EDA. Distributed computing in Spark for training and inference and workflows. And Fandle always had a very cloud-first philosophy. We leveraged Terraform for infrastructure as code. This really helped us in scaling out Databricks, helping with scaling out some of the platforms we use, such as Tecton. So it was really a key differentiator for us. And lastly, of course, Databricks. And Databricks helping democratize the data that we provide by both data engineers and also the data product that we provide from an ML engineering team. So essentially enabling over 300 users to impact the business every day. So another thing to note that is streaming was already powering our analytic use cases. We have streams coming in into our bronze layer in the medallion architecture. Obviously with such a large coverage area of our data, we have different data in different states, time zones, and things like that. Transforming our data so it's usable for the gold layer. And this is where we leverage dbt to essentially build that part of it. But ML brought new challenges and requirements. We needed a feature platform, right? We wanted to model our data specifically for these different use cases, so there were features that were built for the model. We wanted backfills and materializations to reduce overhead, and we had a real desire for real-time serving and batch training. This is very important in sports, as you guys know, because of 24-hour coverage, sports happening in any different location. And lastly, this had to be fully managed because we had a small team, we wanted to be agile. How can we show the most value with that? So our solution was selecting Tecton to build and manage our features. In the OMNI framework, there's many different areas here, and from the data lake into products, we bring in insights, and in the feedback loop, we'll get application data to reinforce some of our models in production. We have the infrastructure, and then the core libraries that power our OMNI framework. We have pipelines that orchestrate the processes in our production ML systems. We have a feature store, and we have services that interface with front-end applications. This is where Tecton essentially powers our feature data lifecycle in the OMNI platform. And has been a big differentiator in making us a lot more lean, providing a lot more value in a short amount of time. So what are the actual use cases? Why are we using data for real time? What are our batch use cases, you might be wondering? So, I would kind of approach this as a defensive and an offensive strategy, right? So for our defensive strategy, we were able to release a production responsible gaming model to enhance the customer experience. There's 71 features powered by Tecton, hundreds of millions of rows of data, and millions of risk scores generated, helping our operational business lines kind of effectively do their job. On our offensive strategy, we're talking more about improving the customer experience, leveraging personalization, and we're able to essentially deploy our daily fantasy recommender, which we found we had a 4% lift over baseline heuristics, and we're leveraging our streaming data sources in providing those recommendations. And it's to note, it's very important to see this use case as this is why we had to use real time, because of the slate locks for contests and kind of the behaviors of our business. And lastly, we were able to serve millions of results on Super Bowl Sunday at a low latency. So if you guys have time, take a look at our product, and you can kind of see the types of recommendations we're providing and powered by some of our framework here. So what does this mean? This is the tip of the iceberg. Recommenders, responsible gaming. Essentially, we were able to accomplish all of these with just 6 ML engineers. We built 3 ML systems in the last 8 months, and we support over 300 people using the tooling we support. There's a lot more on the horizon, and we're just getting started.
Cool. Yeah, thanks, Morgan. And I think that's actually a pretty interesting, I didn't realize this earlier, but 6 ML engineers is, it's not a 100-person team, right? So they have all these other use cases that they have to support. They've got these handful of use cases in production right now, and then now they're able to scale to support what all these other use cases they have in their roadmap, which is a super hard place to get to for an ML team, an ML platform team. So I just wanted to show this slide again to just kind of like remind everybody that this is a journey everybody's going through. It's not, it's not like a binary thing. You get your data together, you start doing some basic analytics. A lot of us are in that, we've built a model and had a model somewhere in production. And many of us are in a business where we now have the ability to, and the kind of like, the purview of taking on a use case where we can use machine learning in real time to get a lot of value for the business. And one of the things that we're trying to do is make that, the barrier to entry for that a lot lower, make it much easier. So you don't need a 100-person ML infrastructure team. You can do it with a team of a handful of ML engineers who effectively become, like superheroes in their organization. So thank you, everybody. Thank you for attending. This is the last talk, I guess. So I appreciate you even still being here. Thank you, and we're happy to answer any questions.